Welcome to lecture 30. In this lecture, I will talk about how to set up fermionic quantum field theories through writing down a path integral for fermionic quantum fields. So far, we've dealt with quantum field theory constructions that were based on scalar field theories. Scalar fields have spin 0, and as such, they are bosons. However, it turns out that most fundamental quantum fields that we have in nature are not scalar fields. The exception to the rule is the Higgs field that was only recently discovered, but most of the other fields that we know about are not scalar fields. There are many examples of scalar fields in other contexts, in particular in condensed matter applications. But in terms of fundamental fields that we have in nature, it is important to consider other properties of fields that are not scalar fields. In particular, it's important to set up fermionic fields, which are half-integer spin fields. To get started, let us review some of the steps that went into our construction for bosonic quantum field theories. In the second lecture, we considered the quantum mechanical Hamiltonian for a harmonic oscillator potential that is reproduced in equation 30.1. We can rescale the operators x hat by introducing new operators q hat that are scaled in the following manner. And if we do so, we can write the Hamiltonian in the form omega over 2 minus d by dq squared plus q squared. We can further rewrite this Hamiltonian by introducing the ladder operators a hat and a hat dagger that is given by the expression 30.3 here. And if we do that, one can verify that the Hamiltonian can be written in the form omega times a dagger a plus 1/2. These ladder operators a and a dagger fulfill certain commutation and commutation relations. And in particular, if we consider the commutator a dagger, then the derivatives are acting in such a way that the result will be non-vanishing. Particularly, we find that the commutator a dagger, when a and a dagger are defined as in the last slide, gives 1, whereas the commutators of the same operators vanishes trivially. One can use the ladder operator to build up energy eigenstates, particularly if we act with the ladder operator a dagger on an energy eigenstate n. We get the energy eigenstate n plus 1 times an eigenvalue square root of n plus 1. Similarly, the action of the ladder operator a on energy eigenstate n gives us the energy eigenstate n minus 1 times an eigenvalue. We can use an anticommutator defined as curly bracket AB being AB plus BA to rewrite the bosonic Hamiltonian as omega over 2 anticommutator A dagger A. We can use this form of the Hamiltonian to calculate the bosonic quantum mechanical partition function, which is defined as the trace of the exponential of minus beta times the Hamiltonian. We can express the trace in terms of a sum of over all the energy eigenstates. And then we can evaluate this expression as we have done in the lectures at the beginnings of this class by putting in the form of the Hamiltonian and find the energy eigenvalues corresponding to this, which, for instance, using the ladder operators, can be easily worked out to be n plus 1/2. The sum here can be calculated in closed form, and we find it's given as 1 over 2 times the sine hyperbolic of beta omega over 2. Let us now try to generalize this concept to fermionic operators, in particular using the bosonic ladder operators that fulfilled this commutation relation. Let us write down fermionic ladder operators that fulfill anti-commutation relations similar to the ones that we had for the bosonic ladder operators. So we define new operators A and A dagger, which have the property that they anti-commute, and the anti-commutation relations are given in equation 30.8. By analogy with the bosonic Hamiltonian, which was the anticommutator, we now write the fermionic Hamiltonian as omega over 2 as the commutator of A dagger A, which using the anticommutation relations can be worked out to be omega times A dagger A minus 1/2. The anticommutation relation implies that the Hilbert space only consists of two eigenstates, 0 and 1. That is because if we want to act with a raising operator A dagger on energy eigenstate 1, we can write this as the raising operator acting on the raising operator of eigenstate 0. But the raising operator squared, because of the anticommutation relation, can be written as 1/2 anticommutator A dagger A. And that itself is an object that's vanishing. So that means that the raising operator on energy eigenstate 1 just gives 0. A similar calculation applies for the lowering operator acting on energy eigenstate 0, so that we find that there are only two states that are possible, the state 0 and the state 1. As a consequence, we can write down the fermionic quantum mechanical partition function as a sum over energy eigenstates 0 of 1 of the expectation value of the Hamiltonian. Plugging in the explicit form of the Hamiltonian, we find that this is given as just two terms, namely the expectation value with respect to 0 and 1. And furthermore, if we assume that these states are normalized, we find that the first term just gives e to the beta omega over 2. And the second state, if we express the expectation value with respect to this term here, we find that this gives e to the minus beta omega over 2. And if we want, we can rewrite this again in terms of hyperbolic functions. Namely, we can write this as twice the cosine hyperbolic of beta over 2. This is the result for the fermionic partition function, and comparing it to the bosonic quantum mechanical partition function, which was 1 over twice the sine hyperbolic of beta omega over 2, we find that in particular the fermionic calculation was much easier because the Hilbert space only contained the state 0 and 1, and the result is a cosh in the numerator, whereas for the bosonic case we had a sinh in the denominator. We can go further into this construction of this fermionic system by defining Bra and Ket states, which are eigenstates of the fermionic operators A and A dagger. We do it in such a way that we define the Ket state C be given as e to the minus ca hat acting on the state 0. And since the operator A dagger is anti-commuting, we can expand the exponential and find that terms higher than the linear term A dagger all vanish. So the exponential becomes just 1 minus c times A dagger acting on 0. And similarly, the lowering operator A on C we defined as just C times the 0 state. Similarly, for the bra C, we define this as the action of the operator e to the minus a c star acting to the left. And we can again write the exponential just as the expansion up to the linear term because of the anti-commutation relation. And similarly, we define the action of the operator A dagger acting to the left as the eigenvalue C star times the bra of 0. Note that these quantities C and C star in these constructions are Grassmann variables. The states that are defined by the Bra and Ket states can give rise to transition amplitude. So if we want to calculate the transition amplitude from C to C prime, we can use the definitions of C in the equation just above to find that this is equal to the expectation value with respect to the state 0 of these two terms. And then using the fact that the action of these operators is given in the equation above, we find that this is equal to just 1 plus the expectation value of A, C prime star, C, A dagger. If we also demand that the letter operators A and A dagger anti-commute with the Grassmann variables C and C prime, we find that we can just pull this through and get a minus sign and sort of get a second minus sign from pulling through the other operator. So we find that we just have that the transition amplitude is 1 plus the expectation value of C star, C prime star C, which we can write again as exponential of C prime star C by using the fact that the Grassmann variables are also nilpotent. Using these definitions, we can then look at the following object here, which is an integral over C star, an integral over C, weighted with the exponential minus C star C of the outer product of these Bryan-Ketz states C. If we again plug in the definition of these Bras and Ketz in terms of just these expanded exponentials, we find that this is equal to the right-hand side here. And now we use the rules of Grassmann integration to limit ourselves to only the terms that are linear in terms of the fields C and C star. And we find that there are only these two terms remaining. One of them sort of gives us the outer product of just the zero state. And the second gives us the integration over C star and C of this object here. Using the fact that the raising operator acting on zero just gives us the state 1, we can write this in the following form and then complete the integral over the Grassmann variables to find that this is nothing else but the sum of the outer product of state 0 and the outer product of state 1. Since there are only two states in the Hilbert space, this combination is nothing else but the unity. So this particular integral over Grassmann variables generalizes the unity relation that we have used and know from the bosonic systems that we have dealt with in the beginning of the lecture. Another integral that we consider is the following integral here that I call IA. It's in the integration weighted with respect to another Gaussian of the expectation value of minus C and C of this operator A hat. And in the following, I'm going to assume that A hat is a commuting operator. So it's not a Grassmann object, it is commuting. Again, expanding the Bryan-Ketz states, we find that this gives rise to the difference between these two integrals here, which again, using the rules of Grassmann integration, we can evaluate. And we find that this is giving us something that is just the expectation value weighted with respect to state 0 and the expectation value of state 1, which is nothing else but the trace of the operator A hat in a Hilbert space that only consists of two states. So this integral IA basically defines the trace of a bosonic operator in a fermionic system. So with these definitions, we now have all the technical tools available to rewrite the fermionic partition function as a path integral. We first use this trace relation that I had on the previous slide to write that the trace of the exponent of minus beta h hat, the Hamiltonian, which is a bosonic operator, in terms of a integral over the Grassmann variables C star and C, weighted by this exponential. And then we can split the exponential here in a product of n pieces, where n is very, very large. We sort of get the familiar form from lecture 3, where we have this parameter epsilon, which is beta divided by n, the number of insertions that we do. Since the Hamiltonian commutes with itself, there are no cross terms, so this relation is exact. Next, we insert unity in the form of this completeness relation in between these different products, where I here is the number of the insertion that we sort of use. If we do that, then we have to consider certain objects that appear in this product. These objects are of the form given in this equation here. So they are expectation values of e to the minus epsilon Hamiltonian in between state Ci minus 1 and state Ci. We can evaluate this expression by using the fact that the Hamiltonian can be written in terms of the operators A and A dagger, and the operator A and A dagger acting on these states Ci and Ci minus 1 have eigenvalues. These eigenvalues are the ones that will appear now in this Hamiltonian function that is no longer an operator, but is a function evaluated at the eigenvalues of the operator A dagger and A. Plugging then in the result for this transition amplitude, we find that this expression here is equal to this exponential given in equation 13.21. And as such, this object takes care of most of the terms in our partition function, except the very leftmost and the very rightmost exponential, which we have to still discuss. If we relabel the C that we had in the definition of the trace as C1, this takes care of the rightmost exponential, and then all we have left is the leftmost exponential. For the leftmost exponential, we have the following object to consider. We have the integral over C1 weighted with the Gaussian times the expectation value of minus C1 e to the minus epsilon h, and the integration over state or insertion Cn with respect to the cat state Cn. Again, we can pull through the integrations and evaluate the Hamiltonian with respect to the states Ci or minus Ci and Cn. This will give us the eigenvalues minus Ci star and Cn for the Hamiltonian function. And again, plugging in the explicit result for the transition amplitude, we find that we can write this whole object in the following form. Plugging or pulling out the epsilon as before, we find that this is the form of the leftmost exponential that we have to consider. And we find that this is indeed of the same form as all the other terms in our partition function, with the only difference that the signs in this expression are not right. There are minus signs that appear. We can formally identify this term with all the other terms in the partition function if we define the n+1 insertion of the field C, so Cn+1 as minus C1, and correspondingly C star n+1 as minus C1 star. Taking everything together, we find that we can write the fermionic quantum mechanical partition function as a product of n integrals starting with, or 2n integrals starting with C1 star C1 all the way to Cn star Cn times the exponential of minus Se, where the Se is given by this object here. It's the sum I1 to n of this combination, where h is the Hamiltonian function that includes the eigenvalues of the raising and lowering operators A dagger and A in its arguments. This result is typically supplemented by the fact that we have to have antiperiodic boundary conditions, meaning that if we look at the object Cn+1, then we have to include for a minus sign that we discussed in the previous slide. As in the lecture 4, we can think of these n values ranging from 1 to n as points on a thermal circle. We can then take the continuum limit n going to infinity, and as such, the entries Ci become a continuous function of a variable that we call imaginary time tau. So tau then will run from 0 to beta, and the Ci's will become a function C of tau, and the Ci stars will become a function C star of tau, with the antiperiodic boundary conditions that C of beta is minus C of 0, and C star of beta is minus C star of 0. In this continuum limit, then, we can write the partition function for the quantum mechanical partition function for the fermions as a path integral over the Grassmann variables c star and c times e to minus this object se, which is in continuum form written as c star dc by dt plus the Hamiltonian function. And this concludes the present lecture.